They're really good evaluators.
You're going to stop recording, then I'll give you
Worth a try.
Worth it. You're always trying, aren't you?
Freeze one apart. He's back on me.
Here, while he's preparing, give me this.
Are you going to get back to your game class? If you give it back to your game class, they'll never do that. They'll never listen to you again.
That's it.
All right, so this foreign individual here, this class, he just showed up from the street and decided to tell me about some very neat. Since you all know about sound, right? Okay, you know about sound. Okay, you know about resonances, right? About velocity of sound and waves and frequencies, right? Okay. So it's going to do something, and it's going to ask you to explain it.
Okay.
And then whoever gets the explanation gets to drink the hot chocolate.
No, I Okay. So this is, it's a phenomenon that all of you can do, and certainly when I do the demos, sometimes I pose this as an interesting observation that you can then go back to your kitchen and actually try to do an experimental test and see if you can really understand what's going on. Basically, we have some glass or ceramic cup that has a nice tone to it, and you just take hot chocolate, any varieties. Probably you should do it without the marshmallows. Just confuses the issue. And then you pour in hot water. Okay. And then you stir it up so that all the powder is dissolved. Okay.
You drink it, yeah.
No. And so what you do now is you stop stirring and you just tap the bottom of the cup. So what's happening?
I'm making noise.
Higher pitch, higher frequency. Okay. Still going up. Now, so it's very high now. Then you stir it up again.
Magic chocolate.
Where'd you get the chocolate from? Exactly. So, again, it's really high now, right?
This is what he does all day.
Now, I should have you know that I observed this a long time ago when I was working as a postdoc at Bell Laboratories, and I showed this trick, or this demonstration, to some of the premier condensed matter theorists in the country, and they had no clue what was going on. After many days of begging me to explain it, I had to explain it to Dr. Sonova.
I'll give you another. I tried. Sonova told me about this, and I went home. But I don't drink chocolate. I drink coffee. So I tried it with a cup of hot coffee. It didn't work.
Didn't work.
Didn't work.
It's not powder. Use instant coffee, but it's not working.
It might work with instant coffee. Did you try it?
I didn't know. I just tried it with regular hot coffee.
So here it is, very high.
Because it's powder and
And it starts out as a low again. So the question is, what is going on? So, suggestion.
Then you spin it back out and you get more fusion.
Magic. Everything is magic.
Maybe the powder's starting to settle.
No, I told you. I stirred up so all the powder is completely dissolved.
Yeah,
And in fact, you can, if you want to, you can look
Making
at
it
the bottom.
homogeneous
There's
solution.
no powder left.
Because you're stirring?
The sound
stirring?
depending on the circuit.
Well, it has, I'm doing something when I stir it up. But let's think of like physicists. You're hearing a sound, so what is the pitch associated with? The frequency, and what determines the frequency? Velocity. Okay, anything else? The wavelength. So the question is, can the wavelength, sir, could you write down the equations for us? My assistant here. So is it possible, now, the frequency is changing by factors of at least 2, maybe 3. So is it possible that the wavelength is somehow changing by factors of 3? I mean, what determines the wavelength in, if I have a string or a rod or
The
geometry, right?
density, the geometry of the cup.
So there's a geometry of the cup that roughly sets some net wavelength. So it can't be the wavelength that's changing. So it must be the velocity.
Maybe when you're hitting it, they can hit it somewhere. Maybe it's the velocity. The velocity. Well, that wouldn't matter if there was some chocolate.
But I mean, we're talking about now the velocity of sound. What does the velocity of sound depend on?
The density.
So is it possible that the density is changing by some factor of 4?
Well, the density as a whole is the same, but in each little, when you tap it, it sends the powder outward, so it makes it a little more dense in certain areas.
But that's just sound. That's sound, but the velocity of sound is determined by the general density, not the disturbance.
Oh, you were saying about the compression?
Yeah.
Yeah. No, that, in principle, there might be some high order corrections due to the change in the density, but, only when you have shock waves, really, do you see these type of nonlinear effects, where the amplitude of the sound is so large.
Is it the volt volume?
Huh?
Volt volume?
Well, okay, if it's not the wavelength, if it's not the density, it's got to be the bulk modulus. Now, what does the bulk modulus mean? What does it signify?
No.
It's the ability for it to compress.
What is that?
The ability for it to compress.
The ability to compress something, right?
So in thermodynamics, you can have the isothermal bulk modulus, and it would be the change in the pressure divided by the change in the volume and constant temperature, and you need some extra factors like that. So that's officially the bulk modulus. And so it's basically saying that if I have some object and I change the pressure, so usually physicists think in terms of the compressibility, which is easier to, which is just 1 over that. So if I have an object and I increase the pressure, the volume decreases. That's why you have the minus sign, so that the compressibility is a positive number. And you divide by 1 over volume just to make sure that it's an intrinsic property. It doesn't depend upon the size of the system. Okay. So you scale out the size. So the question is, why should the bulk modulus or the compressibility change dramatically when I stir up this? And actually now, if I stir it up, the effect goes, it's almost gone. No,
It's just as hot.
it's just as hot. And in fact, again, the bulk modulus is inside a square root. So if the frequency changes by a factor of 4, the temperature would have to change by a factor of 16.
So it didn't go to
Or the bulk modulus would have to change by a factor
1,000
of 16.
degrees.
Yeah. So, we're talking about hot water, boiling point, it's still warm. It's not, it doesn't go from 100 degrees centigrade down to, 5 degrees centigrade in that amount of time. Okay? I don't know. What is different now than it was before? I drank some.
Is it more dissolved, I guess?
No, it's still as dissolved as it ever was. I don't know, did anyone notice what was on top? foam. Now, which is more compressible, water or air? Air. So if I have a volume, okay, that's liquid, but I now have little bubbles on the inside, and I squeeze it, the liquid is essentially incompressible compared to the gas. And so really, when you squeeze on it, you're just making the bubbles smaller. And so if I put enough bubbles into the liquid, the compressibility of the liquid will be almost that of the compressibility of air. And it's more, the compressibility of air is larger, which means the bulk modulus is smaller. And so when I incorporate that air, the frequency goes down. And as those bubbles rise to the surface, the bulk modulus comes back to the bulk modulus of the liquid, and the pitch goes back up. That's it.
So that work with soda?
It will work with soda. It will, unfortunately, maybe I shouldn't tell you this, it will also work with beer. Problem with beer is that the bubbles rise too quickly. And so it's a very, the effect is over quite quickly.
A nice Guinness beer. I'm not looking for a nice Guinness beer.
I just tried it upstairs. If you have like a hot water dispenser.
Not the beer part.
If you have a hot water dispenser, I tried it in the physics nail room, where we have a hot water dispenser. Hot water out of the tap comes in with a lot of air contained in it, but then that air quickly separates out, and you can actually hear for maybe 5 or 6 seconds the pitch change as you tap the bottom of the cup. Now, the best example of this, how many people go to Starbucks or the coffee station in Walker? Nobody. Okay, admit it. Come on, guys. You know, I know you all drink Starbucks, right? When they're making cappuccino and they're frothing the milk, what do you hear? Listen to it next time. Because they're frothing the milk, they're putting air bubbles into the milk, and you'll hear the pitch of this hissing. You know, I don't want to embarrass myself by trying to imitate it, but you can do that. Right. And basically you'll hear that high pitch as they're injecting steam into the milk. The pitch will go down, down, and then when it's ready, you'll hear this really low pitch.
So you screwed up all the romanticism you had about coffee again. You know, you just whenever you go there, you finish the thing now. You cannot get away with it.
Okay.
Thank you very much. Notice the very modern coffee tea maker thing. Right, this one is.
No, that's yours.
Okay. All right.
Have a good day.
Thank you. All right. So now that you can do demonstration outside, too bad.
I told you.